Today we're going to go over Simpson's rule, also known as Simpson's 1/3 rule. It's a way to approximate the area under a curve, similar to a Riemann approximation or a trapezoidal approximation. So the formula for finding for approximating the value of f of x over a certain interval using Simpson's rule is more of a pattern than anything. It's equal to delta x over 3, which is where it gets the name of its 1/3 rule from, plus f of x of 0 plus 4 times f of x of 1 plus 2 times f of x of 2 plus 4 times f of x sub 3 plus ... and so on. And that pattern is going to alternate between 4 and 2, where the last term and the first term begin with 1. So the constants are going to look similar to this: 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 1, or something along that line, along those lines. It depends how large or how many subintervals you're approximating with. But that is what the pattern looks like. The formula or the equation for delta x is equal to b minus a over n. Delta x can be seen here. And n in this situation is going to be equal to the number of subintervals. Okay, we're going to go over practice problem 1 already. We're told to approximate the integral from 0 to 6 of x squared over x plus 1 in respect to x when n is equal to 6. So we're going to start off by finding delta x, which is equal to b minus a over n, which in this case will be 6 over 0 minus 6, which is 1. And now let's assign the value of this integral to L. Now we're going to say that L is approximately equal to delta x over 3, which is going to be 1/3, times, okay, I should mention before I list the terms, that the difference in the x values of each of these terms, such as like f of x sub 0 and 4 f of x sub 1, the difference in those x values is going to be equal to delta x, as you can imagine. So we're going to start off with f of 0. And then we're going to add to this term 4 times f of 1, because delta x is 1. And now we can just list the rest: 2 times f of 2 plus 4 times f of 3 plus 2 times f of 4 plus 4 times f of 5 plus f of 6. Okay, now all we have to do is plug in these values, and it's going to be quite tedious. Okay, so now we can say that this is equal to 1/3 f of 0, which is going to be 0, plus 4 times f of 1, which is 4 times 1/2, plus 2 times f of 2 being 4/3, plus 4 times f of 3, which is 4 times 9/4, plus 2 times f of 4, which is 2 times 16 over 5, plus 4 times f of 5 being 25 over 6, plus f of 6, which is 36 over 7. Okay, we've finally done it. I've already calculated this beforehand. This is equal to, or I should say that L is approximately equal to 13.959. So this is the approximate value, using the Simpson's rule, of the integral given above. Okay, this is practice problem 2. We're given a grid of a bunch of x values and their respective f of x values, and we're told to approximate f of x over the interval 0 to 8 with n equals 4. Now, we of course don't have the equation for f of x, but it's not really necessary. We're going to start off by finding delta x, which is equal to b minus a over n. B in this instance is 8, a is 0, n is 4. So we end up with a delta x of 2. Now we might as well just write out the general expression for this integral, which is going to be the integral from 0 to 8 f of x dx. And we can say this is approximately equal to 2/3 times, and this is the tedious part, times f of 0 plus 4 times f of 2. Now, of course, or as I stated earlier, if you recall, the x value of this f of x term is going to be the difference between the previous one, and that's going to be delta x. Now, our next term in this sequence is going to be 2 times f of 3. Sorry, I don't know why I said that. 2 times f of 4, because delta x is 2. Plus 4 times f of 6. Plus f of 8. Okay, from here we just have to fill in our values for all of our f of x functions, or values, whatever. And we can say that this is equal to 2/3 6 plus 4 times 14 plus 2 times 5 plus 4 times 3 plus 9. And this is equal to 62. So we found that this this integral, the integral from 0 to 8 of f of x dx, is approximately equal to 62. And that's it for today's lesson. The Simpson's rule is not tested on the AP test. I may have stated that earlier. I don't know. But it's a pretty interesting way to approximate the value of the area underneath the curve. Yeah, if you have any other suggestions, of course, put them in the comments below. And please like if you are a fan of this video. Thank you.